Representing high-dimensional data with low-dimensional representations is not only important for data compression, but also important for finding simpler AI models that can give you better solutions. So to that end, we will cover one of the most important topics in linear algebra here, projection theory. So let's move on and understand what's going on. First, let's take from where we left off. Let's imagine that we are in a two-dimensional space, right? So this is my two-dimensional space, and my data points are again like in this two-dimensional space. But I am not interested in. And let me delete some of my data points that could make it look like we're not doing something reasonable, right? So let's assume that my data points are them, and I am interested in remember my Lincoln Avenue example. So I'm interested in representing my data on using only one representation, only one parameter, right? Only one value. So I would like to find my representation on this line, right? On this direction. So I'm going to call this direction my A. Let me not call it yet. Let's call it my Lincoln Avenue, right? And my places are all around the place. And I would like they since they are not directly on Lincoln Avenue, I would like to find their closest uh, representation. They're the closest place that I need to leave Lincoln Avenue, assuming that I can leave Lincoln Avenue at any time. Or I would like to go to Lincoln Avenue to the location that's closest to every single point in my map, and I would like to start yelling to the restaurants, right? I would like to, I would like to find the closest point on Lincoln Avenue to my points in my data set, right? In my places of visit. So we can see this. This is clearly see what's going on, right? We can um, intuitively understand to find the representations of points on a lower dimensional space. But we can also talk about we can also be dealing in three-dimensional world. Let's try to draw a three-dimensional world. Of course, on my two-dimensional space, let me try to draw something like this. Of course, it's not going to be great, but all right, so that's my three-dimensional world, but I am interested in, let's say, so, and I have objects, right? So on this three-dimensional world, let me draw one object. Imagine this is not on the floor, this is just flying, right? So this has some height and some distance from here and some distance from here. Yada yada yada, and I have some other object here flying here in this three-dimensional world, and let me draw a screen, right? And on my world, I would like to draw a screen, and let's say let me draw my room like this, to be like this, and my screen, let me take another color. Let that screen be coming from, let's say, from here, some screen like this, right? So let's assume that, whoops, that the baby blue is my screen. And I would like to find the projections of my objects on that screen, how they would look like, where on the screen they would appear, right? So I'm trying to find kind of the shadows of these objects. So these are my objects. So this is, you see that all of a sudden we go from like finding the closest place to kind of representation of shadows and many more. So this is the maximum that I can draw and we can comprehend visually, we can see visually. But as we saw before, we know that linear algebra can give us good tools to understand how to go from, say, 12,000 dimensions to 768 dimensions, right? So we don't need to visualize, but we can understand what's going on, what is the best. Again, this word best, quote unquote, underlined, italic, and bold. Best with respect to what, but to find the best representation of something in higher dimensions on some space that I know with lower dimensional representation. So, which takes us to today's topic, projection theory. So I'm going to build a projection theory, but let's start simple, right? Let's start with the basics. So I'm going to start with our first example, start from 2 dimensions to one-dimensional representation. Let's first understand, like, be coherent with the terminology. Let's understand what we are talking about. Let's draw a 2-dimensional space. So that's my, I can draw better. So this is my 2D world, right? So and I have a point. Let's draw a point. And if I can find this thing for this point, let's call this the point P. And I'm gonna draw arrows on top of my vectors, because in math, if I'm not typing, if I'm not writing with my pencil, I can type them bold and represent them as vectors. And for scalars, I can represent them with non-bold characters. But since I don't have bold and not, I'm going to draw a bold an arrow on top of vectors that I would like to represent. So this P I know is 2-dimensional because it has P1 and P2, right? So there's P1, P2. And I would like, what I want is, I would like to find on this direction, so that's, let's say this is A. So this is a direction, this is A vector, and that's, again, my Lincoln Avenue. I know the direction, and I would like to find B's best representation. So, sorry. Oh, yeah. Why did I call it B? P. Sorry, I'm gonna call it B because I would like to call the projected vector B. So that's P for projection. So that's my B, and I have B1 and B2, and I would like to find the best representation of B on top of A, and I can clearly see that this can be somewhere here, right? So the shortest path, the best representation on top of A, and I'm gonna call it the P. So notice that P, again, from my God's view, like I can see the 2-dimensional world, but I can represent, knowing A, I know how A goes. I can only say you have to go this much on A to find P. So in order for me to compress all of my B values on 2-dimensional space to a 1-dimensional A direction, which I know how to represent, I only need one representation. So that's my P, and this P again, this is a vector, right? So let me go ahead and write. So my P, my B is in R square, right? So that's my R square, and uh, my A is also represented in R square, but this is just a line. So this is the line. This is the line that I'd like to project to. It's in other words, let me use the proper linear algebra term. So this is A is the basis for the subspace I want to project to. Okay, so that's my A, and B, again, B is R square in R square, and my P. So that um, this guy is also projected. It looks like it is. It's in R square. It has two numbers, but it's a part. It's you see that it's like my all of my projected values. They live on A, so they're not in R square. There are two numbers in P, but I know P is in span of A, right? So P lives on the subspace of A. So that's what's going on. And lastly, I would like to find such an X. So that's scalar. I would like to find such an X such that I can represent the best P as some movement on A, right? So my P, what is my P? What is my projected? And that's some scalar times E. I know A, sorry, some scalars times A. So that's my best projection. So best projection of B on span of A, right? On A. First things first, I know that the error here, that I see the error, so this error is perpendicular. First thing I need to write is error is perpendicular to the subspace. Otherwise, it's not the best representation. Otherwise, it's not the closest one. So, right, that's obvious to us, right? So I know error. So can I write this in linear algebra terms? Of course I can. I know orthogonal. Perpendicular means orthogonal in linear algebra. So I can write my A transpose E is equal to 0. So that's the thing that I'm going to start with. I'm trying to find, how can I find for a B vector and the A direction the best representation of that? I'm trying to find X, right? And I know that X, I can find that X, that gives me the error being perpendicular to E. And what was my error again? Let's look at this error. My error is the difference between, of course, my B minus P. So that's the difference. So I know my A transpose B minus P is equal to 0. Okay, so far so good. And what was my P. My P is nothing but X, the thing that I'm trying to find. So A transpose B minus AX. Again, let me write down these things so that we know what is a vector, what is not, right? AX equals to 0, and I'm trying to find X. And I can write A transpose B minus A transpose A, X is equal to 0. Okay, I'm not gonna write them. I'm not gonna write the arrows. I changed my mind. It's already crowded as is. So I can then find my X to be A transpose B divided by A transpose A. Okay, so we found this, but what is this? First of all, I would like you, so first of all, we are a first thing to notice, what is this? So this is a scalar. I know this is a scalar because this is a inner product, and this is a scalar, and therefore X is a scalar too. So from 2D to 1D. So I was able to find the X on A. The next thing, let's see that I was able to find it via inner product. So inner product actually gives me the best projection. Inner product shows me the closest path. I would like to find A's representation, sorry, B's representation of A. Well, if you want to find that, just take the inner product. Okay, I find the inner product. And the one below that, notice that it's the norm of A. So it's normalizing A. So if we take A to be a unit vector, well, the best representation of a higher dimensional or any dimensional vector on a unit vector is its projection. Its inner product. So that's what I learned. So from this inner product, I learned that if I increase, again, let's look if we can comment on this. If we increase B, if B becomes larger, so if B becomes a bigger version of itself. So like instead of this B, I make this B, right? So if I increase B, keeping its length, you see that um, X becomes bigger too. It makes sense because if I increase B, instead of here, I will be landing here, right? So that's going to be my new B. And if I look at this formula, if I increase A, X doesn't change. So this tells me that A is actually just an idea, right? So X is just sorry, A is just a direction. Like so the volume of A doesn't really matter, the magnitude of A. But if it so happens that A becomes a unit vector, this A transpose A becomes 1, then X becomes A transpose B. So that's the direction. And my best projected representation, so that's P, best representation of B on A is AX, which is A times A transpose B divided by A transpose A. See? That's the best representation of P on A. So this was very mathematical, but it's going to start making sense when we go from one dimension to three dimensions. So let's go ahead and make it three-dimensional. So let's draw our room again. So like I'm gonna draw my room that I would like to project to. And let's assume my projection space is something like this. So that's my space. And I am hoping to find, so that's my number, that's my B. Whoops. And I would like to find B's representation on this space. So let's give a name for this space too. So now I am going to, again, from 3D to 2D. So my B is three-dimensional. So my B is in R cube. And now I have basis function, two basis vectors that makes this space that I'm trying to project to. So I have two directions. I'm going to draw one direction here. So that's my first direction. So let's call this A1. And I have this A2, right? Whoops, what happened to my A2? So that's my A2. That's my new space. The space that I'm trying to project to. And I know, again, I would like to project to this new space. I would like to find my P, my projected. So that's my P. And I know my P has its own values on that subspace. Now I'm trying to find the shadow of B on P. Now, like, I hope at this point you see that this is something related to computer graphics. And I'm trying to find the objects on some space, or I'm changing the camera angle, right? So I'm doing something here that looks like we're not only compressing, we're not only representing my three-dimensional B on two-dimension, like where on that wall of A it is, right? So now I have my wall, my A. So that's my wall. Let me mark my wall. So that's my wall. And my wall is has A1 and A2, right? So I'm gonna call my wall A. So I would like to find how my B is represented on this wall, right? So this wall, and I would like to find my P, which is my representation, and this P is going to be some distance along one direction, and plus some distance along some other direction. So I know it's going to be some x1 times a1 along this a direction, plus x2 times a2, right? Again, let's before we move on, let's understand what's going on. So that's the object, or that's the point that I'm trying to project. Okay, and so this is my two basis vectors of my projection space. So that's the space that I'm trying to project. And these are, so this is just a scalar, and this is just a scalar. And the question is, what is that scalar? What is x1 and x2, right? So let's try to, like, since this is linear algebra, I would very much like to represent it in a simpler way, right? First of all, I can now represent my x like this. I would like to represent my x to be a vector right now. And notice how this is going to be my new compressed vector. I mean, like, if I can find x from B, I know that my projection is going to live on A, and I know it's no longer three-dimensional. It's a good projection on that wall. I no longer need to represent my B with 3 numbers, but I will represent my X with 2 numbers, which lives on A. And if I can write my A is a matrix, so this A1 and A2, so A is A1, A2, so the columns, so they become the columns of A, right? So that, again, like I ended up representing my space with A, right? The column space of A becomes the space that I would like to project to, right? So I can then rewrite this equation, the star equation, then becomes something like this. I know P is equal to AX. Okay, so that's good. So P is equal to AX. And then what is X, right? So again, I can write the same thing. So I know there exists an error. Let me draw the error. So there exists an error of this, right? So this error, I know the error has to be perpendicular to both of my so the error has to be perpendicular to my space. I am not projecting to any location. I'm not going here. I'm not going here. I'm going to directly perpendicular. So I'm going to write the same thing. I know my error is going to be perpendicular to A1. So A1 transpose error is equal to 0. And also A2 transpose the error is also equal to 0, then I can write this A transpose error equal to 0, right? Before we move on, please let us understand that this A is in this example, like going from three-dimensional space to a two-dimensional wall, A is 2 columns and 3 rows, right? So this is A is in R to the 3 by 2, right? So because I have 2 columns and the column space is two-dimensional, I know the projected space is going to be two-dimensional, but the domain is three-dimensional. Any object on that domain gets projected to that wall, right? So I know that's the rule that I'm going to start from. And here we go. We're going to rewrite the same thing. So I have A transpose the error equal to 0. What was my error? A transpose, my error is B minus P, right? Whatever my B minus P is. And A transpose, what was my B? B is B, and P is AX. So now I'm trying to find X. Again, let's remember A transpose is 2 by 3, B is 1 by 3, A is 3 by 2, X is 2 by 1, right? So from this thing, I know how to represent my A, new space that takes from higher dimensions to lower dimensions. That's the direction that I'm trying to find. I know where I start from, higher dimensions, that's B, and I know where to land, that's X, that's lower dimensions, right? And I can write A transpose B minus A transpose A X equal to 0. So A transpose B equal to A transpose A X. And how am I going to leave my X alone? Well, I'm going to multiply both sides with with A transpose A inverse, right? So I will have A transpose A inverse A transpose B. And so this almost looks like solving a linear equation. Remember in our, like, let me draw a thinking bubble here. In our linear equations, it was something like ax equals b. We had something like this, and we could find x equals a inverse b, right? This looks like this, but it's not. So it's almost like this, and well, there's a relationship between the two, and because of the relationship that I will cover very soon, this matrix A transpose A inverse A transpose has a name, and this matrix is called the pseudo inverse matrix, pseudo inverse of A. So I can then understand my best representation than P is AX, which is equal to A times A transpose A inverse A transpose B. And this, my dear friends, becomes the projection matrix. Projection matrix. And typically, the projection matrices are represented with P. So the projection matrix in this form that minimizes the error makes it orthogonal, right? Somehow it didn't like my handwriting. Projection. Projection matrix has two properties. One, idempotence, meaning p square is equal to p. I mean, what you do is p times p. We don't define p square, but it's a simpler way for matrices. Notice that this is a matrix, right? So p times p is equal to p. If we would like to go through that, so if I write this two things next to each other, A transpose A inverse A transpose, again the same thing, A transpose A inverse A transpose. So these guys and this guy cancel each other. So I end up with A transpose A inverse A, which is equal to P, right? So I start from PP, end up with P. What does this mean? It means once you are projected, another projection doesn't do any good, right? Since if you're a shadow, you're already a shadow. There doesn't exist a shadow of a shadow, right? So that's once you are a shadow, you are always a shadow. So that's the first property, and this next property is symmetry. It's even simpler. So the next one is we know it's symmetric. So it's I know P transpose. What? Didn't like my handwriting. P transpose is equal to P. So I would like to talk about this a little bit too, because it also teaches us some nice things. So I know once you're a shadow, let's take one object, one vector that is already on on the subspace. Let's take that's already on column space of A. So I mean, y is already on column space of A, already on the wall. Let me write already on the wall. right? So if y is already on the wall, I know y py is going to be y. So I know that's not going to change anything. And then if I move on, if I try to calculate y transpose, the thing that I'm on, uh, the vector that's on the wall, minus the error, so x minus px, right? So that's x minus the projection of x using the projection. I know this is 0, but I would like to uh, conclude that 0 by following the symmetricity. So I would like to find if it is symmetric, it is going to mean this. So it's y transpose x minus y transpose px. So if I know, since p equals to p transpose, I can write this guy as y transpose x minus y transpose p transpose x. And this guy here is nothing but py transpose. So y transpose x minus py transpose x, and I get y transpose x minus y transpose x, because I know since py equal y, because y is already on the wall. You cannot do anything, like that's from the idempotence. So it's 0. So it means that symmetricity insinuates the orthogonality of the error, right? So this is also like this next part is actually even more important than the first one, the idempotence. I used the first property as a tool to infer the next one. Okay, so this was one example of projection theory. And the good news, I would like to conclude by I started building intuitively from one-dimensional to 2D and 3D to 2D. Sorry, from 2 dimensions projected to 1, and from 3 dimensions projected to 2. So we were able to see what was going on. I'd like to finish by saying that the good news is, even if you start from any dimensions, right? If you would like to project to some space, column space of which you know, and you can write that space, the column space of that projected space, the lower dimensional space, on a matrix, which is a tall matrix, right? So because it's tall because you start from a higher dimensional space and you would like to land on the column space of that. That's you would like to reduce your dimensionality, and you would like to learn your representation. All you need is the pseudo inverse. That said, if you would like to project to that space, you're going to what you're going to do is you're going to find the um, pseudo inverse um, of that matrix, and now you have your representation. Similarly, if you would like to find a projection matrix to project everything, you need that projection. You use that projection matrix to find all of your representations. So that's pretty much it.